Thank you. Okay, so the focus of the work in this presentation is about... Oh, yeah, sorry. Okay, yeah. The focus of my work here is about connecting modeling and simulation tools and optimization tools in Julia. So that's kind of going to be the focus here. In my lab, we're kind of focused on dynamic optimization problems and process flow sheeting problems for this work. So in this presentation, I'm mainly going to talk about these two things, although there are a lot of other applications that we care about. And I apologize in advance. This talk is not like really math heavy. It's more application focused because I'm a chemical engineer. So sorry if you don't understand a lot of the examples. I'm going to try to keep it at a high level though. So in dynamic optimization, we have like a standard optimization formulation, but some of the variables in our system are defined by a system of ODEs. And in process flow sheeting, we have some connection of unit operations, which gives us some system of equations that we want to add to our optimization model. And ultimately, we want to solve these problems to global optimality. And we care about global optimization in my lab because in a lot of real-world scenarios, we're dealing with non-convex problems, which means we need a deterministic global optimizer because we want the best solution to these problems. So here's kind of an example of, don't worry, it's like thermodynamic stability, but what you see is multiple dips in the surface. Each one is a local solution. If you use a local solution method, you may end up operating at this suboptimal point, and you have no idea like if you're doing the best that you can or not. In other examples, you might be like losing money or violating some safety constraint. So really, we want physically meaningful results when we're dealing with these types of problems. So we need deterministic global optimization. Here's that kinetic parameter estimation example again. So in this example here, we're trying to estimate 3 kinetic parameters that appear in a bunch of the differential equations, and we do that by minimizing the sum of squared errors. And I kind of made this image a bit bigger so you can actually see it, hopefully. So if we use the values obtained at a local solution, which is the dashed curve, then we see that we're not exactly in line with the data or the global solution. So we're not really sure, like, are we operating at or like what's wrong with our model, or are we using the wrong parameters? But you don't really know because you're not using deterministic global optimization. So these are the kind of problems we're trying to deal with in my lab, but how do we solve them? So typically, a lot of chemical engineers will write their own solver every time they want to solve a certain type of problem. And that's what we've done. So we developed Ego, which is a deterministic global optimizer that's written entirely in Julia and written around JuMP and MOI. What makes us different from other global solvers is that we're entirely open source, and we're written in Julia, right? We're one of the only global solvers written in Julia. I should need to convince you guys to use, JuMP or Julia in this audience, so I'm not really going to go into all that. But because, we're written in this ecosystem, we can provide great extensibility features and, a user-friendly way to write and solve optimization problems to global optimality. And we've compared Ego to other solvers in the past, and we've, seen improvements compared to like Baron or Antigone. But we're kind of a pretty good general solver. It's not like for specific problems, just like any problem you want to solve to global optimality. But it's also a research platform. So similar to what Oscar said about the automatic differentiation in JuMP, we kind of modularize the global optimization algorithm so that users can, take up one part of the algorithm, and maybe they want to implement like a custom lower bounding problem, so they can do that if they really want to, without having to rewrite the entire algorithm or write their own solver from scratch again, which seems to be what people love to do. And here's just some recent advances that we've made to Ego. The most recent one is a custom implementation of an LP solver on GPUs. This is kind of the first implementation for LPs on the GPU, or for LPs for deterministic global optimization. It's a bit different than the standard PDLP because that uses that's for large-scale systems, but in global optimization, we're worried about small-scale systems. I'm not really going to go into that too much in depth, and that I don't have a citation for that because that paper's still under review, but you can check out Ego if you want to. But don't Google Ego because you may end up buying a toilet or something. I don't know why they chose that name. So we have our global optimizer and we have our dynamic optimization problem. So why don't we just plug it in and solve it? Well, if you're familiar with JuMP, then you know that we can't just take an ordinary a system of differential equations and plug it into a JuMP model. And the JuMP documentation says maybe you should use something else, but I want to use Ego because I wrote this great solver. So how would I end up doing that? Well, really you have to have knowledge about how to discretize a system on your own, or use some package that does it for you. And then you have to use the right step size. If you're dealing with a stiff system, you're going to have a lot of problems. Or you have to reformulate your problem if you want to use it in a JuMP model. but really, I guess we can't use JuMP for dynamic optimization the way we want to in this case. So that's one of our problems. The other problem I'm going to talk about is process flow sheeting. So in these types of problems, we have some model that we've modeled in some modeling language, and then we want to simulate it and then add those equations into our optimization model. Don't worry about like what all the things are in the picture. They're just a bunch of unit operations that do various things, and the arrows just connect the streams together. So there are really two main approaches to doing modeling and simulation. So we have causal, sequential, modular, and acausal or equation-oriented. So in the causal approach, we have to kind of derive an explicit representation of the outputs in terms of the inputs. So we have to like go through each stream and each unit operation to define that relationship. Whereas in the acausal approach, you just have to write down your system of equations, then you can solve it using whatever numerical solver you like kind of instantaneously rather than having to derive that relationship every time. The causal approach is kind of the standard way people are taught in engineering, but the acausal approaches are shown to be way better at large-scale systems, and having a system of undirected equations is more flexible in your design. So in this example, we have a reactor into a separator, but what happens if we make a change to that system? Well, for the causal approach, we have to go through and derive our relationship of inputs and outputs all over again, which is kind of cumbersome, and it's more computationally expensive for a computer to do it. But in the acausal approach, we just have to add that other equation, and then we solve the problem, using a fast numerical solver again. So generally in practice, we want to use an acausal or equation-oriented modeling language when we're trying to model these process flow sheets. There are a lot of packages that do this, but really in Julia, there's only one that does this really well, and that's ModelingToolkit. It's part of the SciML ecosystem. So it allows you to basically build these process flow sheets, but one of the really great features they have is that they can automatically reduce the size of a system, because generally when you're building a process flow sheet, it's very easy to make a very big system, and you have a bunch of equations, which means it takes a long time to simulate. And if you have a lot of equations, it takes a long time to optimize that if you're doing global optimization. But they have this amazing structural simplification, which is kind of unique to their package. Other modeling and simulation packages can't do that. And we want lower dimensionality problems for faster simulations and for less variables in optimization. So here's kind of an example of a model built in ModelingToolkit. Just we can just write code that defines each of these streams and components, and then we say how we're connecting them together, and ModelingToolkit will automatically create the system of equations and then reduce it if we want it to. And this is what we call componentized models. That's kind of what I'm going to be referring to them as later. I'm going to use the word model a lot, but sometimes I'll be talking about a JuMP model. Sometimes I'll be talking about a ModelingToolkit model. So now we have a tool that we can use to, model our process flow sheets and simulate them, but we still can't use them for optimization, really. But maybe we can, because ModelingToolkit is part of the SciML ecosystem. And again, the documentation here says we should use differential equations or optimization.jl, which are both part of the same ecosystem. So maybe we could use that for optimization. Well, we can't actually. We can do ODEs to local optimality in optimization.jl, but we actually can't use the componentized system I just mentioned. The only way to really do that is to decompose it yourself and then rewrite the causal representation instead of using the macros that they've built. So you kind of lose all the benefits of being acausal, and it's a lot more manual work, which we don't want. And even if we use optimization.jl, we don't have deterministic global solvers in there, so we still can't solve the problems the way we want to. So in summary, right, we can't solve dynamic optimization problems or process flow sheeting problems in Julia the way we want to. And we really want to make use of both of these ecosystems. So we can do modeling and simulation on one side and then use good optimization tools on the other. But these packages aren't compatible, right, because one's written symbolically, another one's written in MathOpt interface. So how do we kind of leverage the capabilities of both ecosystems and combine them together? Well, really, you have to do it manually, right? You would look at your simulation output from ModelingToolkit, and then you would manually translate that into constraints for your JuMP model. But you can just think how difficult that would be when you're dealing with large systems and you have to do this multiple times back and forth. So we're introducing a way to do this automatically. So we developed this abstraction layer package. It took us a while to kind of land on a name here, but we're going with eOpt interface, or EOI, which allows us to automatically generate JuMP constraints from ModelingToolkit models. So now we can connect these two packages together, or ecosystems together. And this is kind of the workflow we put together for how we expect the package to be used if you're doing this sort of work. So you start by formulating your problem. It could be dynamic. It could just be a componentized system, and then you write it in Modeling Toolkit to automatically simplify it, reduce the number of variables and things like that. And then we can use the apt interface to make a JuMP model, then use whatever optimizer we want if it's applicable to that type of problem. And then even after that, once we have our solution from JuMP, we can send it back to Modeling Toolkit to figure out what the full space solution would be. So I have just an overview of some of our features. So we automatically generate the constraints, and then obviously we need some sort of direct transcription between for ODEs. You need some way to deal with ODEs essentially, but I'll talk about that in a bit. And then we also have something to display decision variables, because we want to know which variables Modeling Toolkit has left in the model, so we know what bounds to use when we're making our JuMP model. So I have a few case studies kind of going through the stuff we've done. So the first one is, again, this dynamic problem. So we just take our differential algebraic system and write it as a Modeling Toolkit component. And then once we have that component, we can discretize it using one of the methods we've coded up. Pretty straightforward. We have a few methods for this. We have more than just that, but I'm just showing a few here. But like I said, there are a bunch of different ways to do this, and like, why do we do this if other packages can do this? For example, SciML has kind of exposed 3 or 4 backends. It's kind of hard to say for sure, but one of them requires you to use infinite ops. So instead of building a JuMP model, you're actually building an infinite op model. So it's kind of like we have to add another dependency into this whole thing if we want to kind of use this framework, but it gets way too complicated if we're adding in multiple packages. We just want a simple way to transcribe our system, and the other way would be to generate relaxations for dynamic problems, and we have another package for that doesn't really apply in this case. So yeah, that kind of shows that we can directly transcribe ODEs, which is a necessary component. But the next example is kind of way more applied. Again, it's that process flow sheeting example, but I've kind of simplified it. Here we have A reacts to B and then B reacts to C, but we really want to produce B. We don't want C, so we want to produce some minimum amount of B. So that's one of our constraints. And our objective here is to minimize the total cost of the system, and we have a few parameters that we can mess around with in our design. So we can follow this workflow again. We make our model, put it into Modeling Toolkit, then send it to JuMP and Ego, then send it back to Modeling Toolkit. So these are kind of the results for that system. We have the full space is 50 variables, while the reduced space is 6 variables, and you can see a huge difference in the amount of time it takes to solve that problem. And we couldn't do this if we were using JuMP alone, unless we had some advanced pre-processing stuff, but that doesn't really apply to a system of algebraic equations on its own. And this is a steady state example, but it still kind of illustrates the importance of reducing the size of your system for global optimality. But you can imagine a case where that reactor is not at steady state and you have a system of dynamic equations, so now you need to use both features at once. So my third example is, I'm not going to go too crazy with that one because it's a bit advanced, but it just showcases combining both of these features to do an MPC problem. So these are the kind of examples that really motivate the problems that we're trying to solve in Ego and in my lab. So this is like why we develop Ego the way we do. So we have this massive process flow sheet of a wastewater treatment plant, and ultimately we want to model it, simulate it, and then apply advanced control systems to it. But in this case, so eventually we'll build a Modeling Toolkit model for the entire thing. But in this small example, we can just look at one reactor in the entire thing. So I'm not going to go into the specifics of the mechanistic model we have, but it's 10 to 20 ODEs, and we have a bunch of parameters in those. But the MPC is you simulate your system, and then you send that to your MPC optimizer to figure out your optimal controller action of maybe like opening and closing a valve to add more add more air to the system. And then you kind of repeat that cycle over and over again just to keep your system running. So like with the apt interface, we can combine Modeling Toolkit and JuMP to do closed loop real-time control. And the alternatives to doing that would be like using Python or some other package, but we don't want to use those because we don't get the unique functionality of the things in Ego or the things in Julia, JuMP, and Ego. So those are kind of the 3 examples I have to just illustrate what we've done. You might not use this package because it's very applied to what we do in chemical engineering, but we have this package. We hope to release it soon. We just have to publish our paper. In our future work, we have a dynamic optimizer that was written in like Julia 0.7, so we have to update that so we can use relaxations for these types of problems. But that's something we're looking forward to in the future. Yeah, so with that, I would have to thank my acknowledgments, and I'll happy to take any questions.